All right, yet another video lesson here. This one is focusing on tangents, arc measures, and chords. Okay. Identify for the bell work each of the following. So I give all of the pieces that we discussed with the last section of the overview of circles, and I just want you to name all of these pieces. Okay. Notice that I do not specify the number of them, so there are a couple options. I am going to put all of the options that you have, okay? But depending on how I ask the question, I may ask for only one of them, or I may ask for all of them, okay? So make sure you pay attention to what it's saying. So here, number one, name the chords, okay? Chords. So I have several. I have chord FE, or EF. Okay. That is again the line segment. It is a chord. I have here EG. Again, it is a chord, so it's a line segment. Something else here, I have A to D. Okay, and then I don't have any more chords in here. Again, remember, a chord is a line segment whose endpoints are both on the circle. Okay, so I only have 3 lines that go from one side of the circle to the other side, okay, or from one spot on the circle to another spot on the circle. Okay, number 2, name the tangent. If we look at the visual here, we only have one line that goes and touches the circle and then goes away. It does not go through the circle. Okay, again, a tangent is one that touches and goes. So here I have options here. Okay, I'm going to give 2 of the options because again I can flip the first one. Okay, so I have a point F and a point H. So my alphabetical order here. And again, this is a line, so you have to have the line with the arrows above it, indicating again that it is a line, not a line segment. Okay. The other option here is again, then I had this italicized letter here on the side. This would be then line S. Okay, again, 2 options here, but again, you have a third option with that F and H being reversed. Okay. Number 3, name the circle. Again, to name the circle, you have to look at the center point. And that center point here is that value of C. So here I have to have the circle with the dot in the middle, and then that letter. Okay, so circle C. Number 4, name the radius. Okay, here I did not say name the radii, so I'm not asking for all of them. However, I am going to list all of them that I see. Okay, so first one here, I'm just going to start here, and I'm going to work my way around. So here I have this line segment, which would be CE. I also have this line segment, which would be AC. I also have this line segment from C to B, so BC. I also have this line segment from C to G, so CG. And then I have another one from C to D, so CD. Okay, so again, 5 different options here, which turns into 10 different options if I reverse the letters for each of those. Okay. Number 5, I'm going to name the diameter. Again here, I have 2 options actually. Okay. I have AD, because again it goes from here to there, and goes through the center. And then I have from E to G. Again, EG goes through that center point of C. Number 6 there, name the secant. Again, this is a geometric secant. we have several options here. So notice that I have now 3 dots on that secant line. So I have the point A here, I have the point C, and I have the point D. Okay, but then I also have this italicized letter here, V. So my options here would be A, C, with the line with the arrows on top. I could also say AD, again, line with the arrows. I could also then use CD, line with the arrows. Okay. Or I could say line V. Again, those 3 that I say, AC, AD, and CD, you could reverse those letters, but again, I prefer your answers to be in alphabetical order. Okay. No, you will not be docked if they are not, but again, I prefer it to be that way. Okay, moving on to the content here. We do have 11 pages of notes to go through here. We're going to cover several things. Obviously, this is not a complete overview of circles. However, it does touches on some of the key components. Okay, so here the focus on tangents. Although there are a number of things that we can focus on, again, we're going to focus on just these 2 items here. The first thing is the perpendicular tangent theorem, and the second thing is the intersecting tangents theorem. Okay, first thing up here is the perpendicular tangent theorem, and that just states that a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. Okay, so in other words, if I'm looking at number 1 here, that statement says that AB is tangent to circle C if and only if it is perpendicular at point B, or the point of tangency. Okay, so perpendicular means what? Perpendicular means that this has to be a right angle here. Okay, and we have to think back about the things that have helped us out as far as perpendicular or right angle and theorems and stuff that we've discussed. Okay, and the biggest theorem that should come to mind here is Pythagorean theorem. All right, and that's how you're going to check these. So you're going to take the 2 legs and square those and add them together, and that should equal the hypotenuse squared. So again, the Pythagorean theorem is a squared plus b squared equals c squared. Okay, and again, it's important that you plug these into the correct letters and make sure that you're doing this appropriately. Okay, so again, the 2 sides that touch point B here are my legs. So CB, or 7, is either A or B. I'll just put it in for A. Plus BA is then now the other leg, so that's the B value. So this is 13 squared. And that should equal the hypotenuse squared. Okay? If in fact this holds true, that the left-hand side is equal to the right-hand side, then these are tangent. Okay? If it is not true, if it does not equal to each other, then you would put the strike through the equal sign, indicating that they are not equal, and then you would write the words not tangent. Okay, so let's work it out. 7 squared is 49. 13 squared is 169. 20 squared is 400. And if I add the left-hand side together, I get 218. And that equals 400. Okay. Obviously, that's not true because 218 is not 400. So these are not equal. And then you would again write the words not tangent. Okay, so on every one of these problems, I'm going to ask if they are tangent or not. And then I'm going to have the word explain, okay, next to it. And your explanation is the work from the Pythagorean theorem. You just have to show this work here for your explanation. I do want to see again this little slash through the equal sign, indicating that they are not equal. Okay. Number two, again in a similar fashion here, what this theorem is saying is that if line AB is tangent to circle C, then at the point of tangency, or at point A, there has to be a 90-degree angle. Okay, so we need my right angle here. So again, I'm going to use Pythagorean theorem. I have this line and this line are now my legs. So 15 squared plus 36 squared should equal 39 squared if line AB is in fact tangent to circle C. Okay, so if I take 15 squared, I get 225. If I take 36 squared, I get 1,296. And if I take 39 squared, I get 1,521. And when I simplify on the left-hand side and add these together, I do get 1,521 to equal 1,521. That means that these are in fact tangent. Okay, so again, my explanation is this work here, and then the word tangent seals the deal. Okay. Moving on to the next theorem, the intersecting tangents theorem. Okay. Intersecting tangents theorem just states that any tangent segments that come to a common external point are congruent. Okay, so for instance here, let's identify these as some letters here. If I had this as point A, this is my common external point. This is a point that's outside the circle where these two lines that are tangent connect to the circle but outside. Okay, so let's call this point B, and I'll call this point C. Okay. All right, so what this indicates to me is that I should be able to take my two expressions here and set them equal to each other, okay? Because it states in the theorem that they are congruent, and congruent means that they are equal. So 14x plus 18 is equal to 3x plus 29. Okay, and then what should you do with this? As with any equation that we can solve, let's solve it. Okay, again, it's the game of opposites. I need to shift things from one side of the equation to the other. So here, to try to keep my x's positive, I'm going to subtract 3x on both sides. Okay, I'm going to do this one piece at a time so that we can make sure that we understand it. Again, some of you are going to have to be your own advocates here. If you can shift a couple things around at the same time, by all means, go ahead. Okay. But we're not going to in the video here. 14x minus 3x would be 11x. This 18 comes straight back down because I didn't mess with that at all. That canceled. Equal sign. And that's positive 29. Okay. Now again, the end game here is the idea of getting the x alone. So I need to move that 18. So I'm going to subtract 18 on both sides now. The 11x comes down. This is now canceled, 0. Equal sign. 29 minus 18 is 11. I now need to get that 11 off the x, so I'm going to now divide by 11 because that's multiplied, which then gives me x equals 1. Okay, things to pay attention to with these problems. I'm going to ask these in one of two possible ways. Okay, the example here, I simply ask you to find the value of x, which we've done. Okay, which means that this problem is actually finished. However, in some other problems, I might ask you find the value of AB. Okay, so for example, let's do that. If I found the value of AB, what I'm going to do is find the value of x because I need to plug in x into this equation. So AB equals 14x plus 18. But I've now found that x equals 1. So then AB is equal to 14 times 1 plus 18. So then AB is equal to 14 plus 18, which means AB is now equal to 32. Okay, and you should be able to plug into the value of x for AC. And again, the fact that these are congruent means that AC should also work out to be 32. Okay. The next topic here, arc measures. There are a number of things that we could discuss about arc measures, and again, we're just going to focus on a few of them, these 5 in particular. Okay, a central angle. We're going to talk about several different kinds of angles in circles in relation to them, so you're going to have to make sure you keep them separate from each other. Okay, a central angle, a minor arc, a major arc, a semicircle, and the arc addition postulate. Okay, there's more notes here to go through. Definitions are important here. A central angle is an angle in a circle whose vertex is the center of the circle. Okay. In other words, I have a circle. And I have my middle point here. Let's call it A. And what this is saying is that I have an angle that connects at the vertex at the center. So the vertex is just that point of the angle. So if I have this angle here, and let's call this BC, then angle BAC is a central angle. Okay. Or again, I could flip that and call it angle CAB, and that is also a central angle. As long as A is that center letter of those 3, then we can call that the central angle. Okay. A minor arc is an arc that is less than 180 degrees. Okay, and it is called by its endpoints, and I should have a little arc above that. Okay, so if I'm looking at that example that I just did on the first thing there for central angles, then BC would be a minor arc. Okay. A major arc is an arc that is greater than 180 degrees. Okay. Also, again, named by its endpoints, and one point between. So here I should again have that arc above ABC. And then we have the good old semicircle, and a semicircle is half a circle. That's what semi means, half. That equals 180 degrees, because again, a full circle is 360 degrees, and if I take half of that, I get 180. Okay, so we have a combination of things here. To find a minor arc, then that minor arc is equal to the measure of the central angle. Okay, and for a major arc, we have 2 options here. Okay, option 1 is to take 360 degrees minus the minor arc. Okay, so let's say I have only 2 pieces of a circle, and I have one big arc and then one small arc, I could just take 360 minus that small arc and then be done. Okay. However, other spots I'm going to have just a whole bunch of minor arcs that we're going to go ahead and add together. Okay. So again, you have to look at what kind of situation you have. Okay. So here, arc addition postulate states that if you want to find the measure of an arc formed by two adjacent arcs, okay, and adjacent here means that they are touching or connecting, then the sum of the measure of the two arcs is the measure of that arc as a whole. Okay, so I'll talk about those in a second. So dB, arc dB is equal to what here? So arc dB, let's do in blue, and I'll highlight it here. Okay, it goes from D and it goes straight to B. If I give you two letters on the arc, that will typically mean that you only have a minor arc. Okay, a lot of people are going to want to look at this and say, okay, well, I can go from D and I can go backwards and go to B. Okay, this is not a minor arc. This is obviously, or hopefully clearly, more than 180 degrees. It's more than half of that circle. Okay, so if I give two letters, again, strong emphasis here, you are only going to go with the minor arc, the smaller of the two. Okay. Here we'll notice that we have 35 degrees for this section here. And hopefully you can tell that at point C, this is the center of the circle, which means from AB, this is a diameter. And because that's a diameter, then this half is a circle, a half circle, and this half is a half circle. So the value of dB is going to be equal to 180 minus the 35 degrees that we have. Okay, which gives me 145 degrees. Another thing that I'm going to expect you to do as well when you do these and find the value of them is that you're going to have to classify them as well. Okay, so if I look at 145 degrees, I have one of, again, three options as far as my classification. I could have a minor arc, a major arc, or a semicircle. Okay, because this is only 145 degrees, it is less than 180 degrees. That would put this as a minor arc. Okay, DAB. Now, we have three letters, and it has to go through that process. You cannot go from D to B, around to A, and then back to B. It has to be in connecting fluid movement. So I have to go from D to A and continue on to B. Okay, so I want this entire section here. And again, as stated with the previous problem here, that whole bottom portion here, from here all the way over to here, that's a half of a circle. So that's 180 degrees. So we're going to use that 180 again here. And then here I'm going to add, because I had this in addition to that. So the plus the 35 degrees. And if I combine those two together, I get 210 degrees. And again, in order to finish this, I'm going to classify 210 degrees, 215 degrees. Let me make sure I get that correct. Okay, 215 degrees. Again, I need to classify. So I have minor, major, or semicircle. This is more than 180 degrees. So this would be a major arc. Okay, and for the last one on this page, ADB. Again, I'm going to change the color here, so now I'm going to overlap here. I'm going to go from A up to D, and then continue on to B. Okay, so I went on the outside here so that we can continue to see those different colors here. So from A to D to B, you'll notice is actually that full half of the circle. So we have two options here. I could do the 35 degrees plus that 145 degrees from DB, which would give us that 180 degrees. Or I could just again see that that's half of a circle and then say it's 180 degrees. Okay. Again, then I need to classify that. So not major, not minor, because it is exactly 180 degrees, which then makes this a semi-circle. There you go. Okay. On to the next. Focus on chords. We now have two theorems to focus on with chords. Okay, these theorems that we're going to focus on for this curriculum is the perpendicular bisector chord theorem and then the congruent chord theorem. First up is the perpendicular bisector chord theorem. Okay, that's a lot. We have one of two things here. Either A, I give you that the chord is a perpendicular bisector, which means what? Okay, perpendicular indicates to me that they connect at a right angle. Okay, and bisector means that it would split it in half. Okay, so if one chord splits another chord in half at a right angle, then that first chord is in fact the diameter of the circle. Okay, or statement 2 here says that if I give you the fact that we have the diameter and I tell you that it is perpendicular to a chord, then that not only does it bisect that chord, but it also bisects its arc. Okay? So here we have to figure out which of the two examples or sets that we have. So in the diagram, circle C, it says find the length of BF. Okay, again, I can present all kinds of questions on these. I can present these in all kinds of different ways. Here I give just a simple value for DF, okay, which we're going to use. But I could give you expressions, so make sure you pay attention to that. Okay. But here, notice that I give you the fact that this is a diameter. I give you the center circle here. You have the whole length here, that's the diameter. And I indicate to you that this is perpendicular. Okay? That's that second scenario, which then tells me that this segment from here, from D to F, is then congruent to F to B because that is a perpendicular bisector. Okay. It would also indicate to me that arc DA is congruent to arc AB. Okay, so I don't use that a lot in my class as far as the worksheets go. However, know that that is an option on any kind of standardized test or any future geometry stuff that you guys get into. Okay, but because this fits the second part of that theorem, that this is the diameter and this is perpendicular, then we know that DB is bisected by the chord or by the diameter AG, which means that if this is 25, then from B to F is also 25. Okay, again, a diameter that is perpendicular to a chord makes it bisect that chord or splits it in half. Okay, and the last section of this, the congruent chord theorem. Notice that this one's kind of a lengthy one, but again, bear with me. The theorem says in a circle or congruent circles, okay, so I could have two circles that are side by side or on the opposite sides of the paper here, then two chords are congruent if and only if they are equidistant from the center of the circle and perpendicular at the point of intersection. Okay, so what does that mean? That means that on this circle here, that these two chords from Q to R is congruent from S to T. If and only if we have the two scenarios, I have to have VP be congruent to PW in length, as well as I have to have at here, at V, a perpendicular intersection, and at W from the center of the circle. Okay, so they have to be equidistant and perpendicular at the point of connection from the center to that chord. Okay, so what this tells me is that in the diagram, circle P, PV from here to here, as I indicated, is equal to PW from here to here, as I indicated. Then QR, I give an expression, and ST, I give an expression. I want to find the length of QR. Okay, but from the theorem, what this is telling me is that these two expressions are then equal to each other. Okay, so again, I'm just going to set them equal to each other. 8x minus 12 should equal negative 2x plus 8. And again, as I have as an equation, I'm just going to solve that equation for x. So I'm going to add 2x here. I'm going to add 2x here. Okay, and again, bear with me. I'm just going to do it one piece by one piece. This gives me 10x minus 12 equals that 8. I'm going to move the 12 now. 12's cancel. I give 10x equals 10. 20. I didn't see the 1 there. 20. I'm going to divide then by 2. Goodness, I'm trying to go with the answer already. I'm going to divide by 10, which is going to give me 2. Okay. But then the question is, did I actually in fact answer the question that was asked? So make sure you pay attention to that. Did I only ask for the value of the variable? Okay. And the answer to that would be no, because it states find the length of QR. Okay, so once I find the value of x, all I'm going to do is go back and find this expression here for QR. And I'm going to rewrite it. Okay, so QR is equal to the 8x minus 12. And we just indicated that the value of x is 2. So I'm going to plug that in. So 8 times 2 minus 12. So then QR is equal to 16 minus 12, which means the value of QR is in fact 4. Okay. As always, if there are any questions, comments, or concerns, by all means, feel free to reach out and let me know.